the factor theorem is a direct result of the remainder theorem. Recall factor is a term that when you divide it into another polynomial, that there's no remainder, or the remainder equals zero. So the factor theorem ties zeros of a polynomial, or inputs that make the output zero, with factors directly. And it says that for any polynomial, p of x, that k is a zero of this polynomial if and only if x minus k is a factor of p of x. K is 0, that's equivalent to saying p of k equals 0. So this combined with the remainder theorem allows us to solve problems like example 3, where using long division or synthetic division are hard or impossible. But by knowing something about zeros and factors, that we can still solve these sorts of things. Like for example, given that x minus 2 is a factor of this polynomial, where we know each of the terms except we don't know the coefficient from x squared, we can figure out what k is and then fully factor or factorize it. It's tempting to take x minus 2 and do long division and try to approach the problem in that sort of fashion. And it might be possible to do it that way, but it's going to get really complicated in a hurry. However, using the factor theorem, this is pretty efficient. So the factor theorem tells us that since x minus 2 is a factor, this tells us that p of 2 equals 0. Meaning that if I substitute 2 into here, the answer is 0. So 2 to the third plus k times 2 squared minus 3 times 2 plus 6 equals 0. Or better yet, 8 plus 4k minus 6 plus 6 equals 0. 8 plus 4k equals 0. K equals negative 2. So we found the value of k, and now we should be able to factor this, because we know that x minus 2 is a factor of this thing. So if I plug in minus 2 in for k and use some form of division, whether that's a long division or a synthetic, to divide x minus 2 out, I'll be left with a quadratic. In those things, we have lots of easy techniques for factoring those. So let's do this. I'm going to replace negative 2 in for k. X cubed minus 2k squared minus 2x squared minus 3x plus 6. And I'm going to use division to divide out x minus 2. Again, you could use synthetic division if you want. I'm going to use long division. And since this is a factor, I know what the range is going to be. It's going to be 0. And we'll check to make sure that's true. Let's see. Division algorithm. X times x squared is x to the third. So multiply by x squared, I get x cubed minus 2x squared. Subtract. I get 0 and I get 0. Bring down the minus 3x. And also bring down the plus 6. I need to multiply x by minus 3 to turn it to minus 3x. Minus 3 times x is minus 3x. Minus 3 times minus 2 is positive 6. When I subtract, what do you know? I get 0. What this tells me is that this polynomial can be written as x minus 2 is a factor, and x squared minus 3 is also a factor. And you can factor this further by using the difference of two squares. X. 3 doesn't have a perfect square, but no harm, no foul in using the square root. Okay. Putting these things together, the factor theorem and the remainder theorem, we come to the most general form of them, which is called the fundamental theorem of algebra, which you may recall from Algebra 2 and Pre-Calc, which says that a polynomial of degree n has n roots in the complex numbers. I highly recommend checking out this number file video. It's fantastic, and it talks about a really a geometric and intuitive approach to understanding why this is true and why there should be this many roots. So give it a watch when you get an opportunity. That being said, we'll kind of use some ideas of the fundamental theorem along with the factor and remainder theorems and what we know about complex numbers to try to answer this question. Where we have a polynomial. I don't know what these two coefficients are. They're both the same, and they're both a. It's a third degree polynomial. Oops, and I forgot I mistyped this. That should be 9x squared. And I know that this complex number, negative 3 plus I, is one of the roots of this polynomial. Knowing this, we can find all the roots. We can find a and then each root of this polynomial. So this is my thought process. I think that since p of x is a real polynomial meaning that the coefficients are real numbers. What this tells me is that zeros come, if a complex number is a zero, it comes in with its conjugate pair, is another zero. Then since z equals negative 3 plus I is a root, then z star, or the complex conjugate of z, minus 3 minus I, is also a root. What this means is that, what this tells me is that I know two of the three linear factors of this cubic. They're x minus z and x minus z star. Or multiply this out, because I know what z and z star are. I know that x minus 3 plus I and x minus 3 minus I are roots. So I multiply this out, as we've done a few times already. If I do my trick of turning this into a difference of two squares, this is equal to x plus 3 squared minus I squared, which is x squared plus 6x plus 9 plus 1, or x squared plus 6x plus 10. What this tells me is that this quadratic is a factor of my original polynomial. What does that mean? That means that what this tells me is that this polynomial, a times x cubed plus 9x squared plus ax minus 30 is equal to x squared plus 6x plus 10 times some linear factor. There's going to be some linear factor where there's something times x plus some other term. So if we can figure out what these are, we'll know the last term. Let's see. I think we can deduce what these have to be. I think that whatever this orange thing is, it has to be the same as a. Because in order to get the x cubed term, I'm going to take this term and FOIL it to this x squared term. So whatever this is, it's a. I think this blue term, we can figure out what this blue term is, because this blue term, when I when it multiplies to 10 is the only way to get a constant term. So what do I need to multiply to 10 to make the constant term? And I think what needs to get multiplied together is with a minus 3. So I can deduce that this last term is a minus 3, for sure. Knowing that, I can figure out what a is. I know that if I FOIL a times x squared, I get this first term. There's also an a in this linear term. So if I FOIL this out, I can also match up whatever the term is in front of that's the linear term, and I can equate those two things. So I'm going to do that, as well as other things in the a. So I'm going to FOIL this out. So I know that I'm going to rewrite this first term. A x cubed plus 9x squared plus ax minus 30 is equal to, let's see, the x cubed term is a x cubed. See, what's the x squared term? The x squared term should be 6a and minus 3 is going to be the coefficient of x squared. I think the coefficient in front of x should be 10a and minus 18. And the linear term is 10 times minus 3, which is minus 30. So coefficient, if these polynomials are equal, then these coefficients in front of like terms need to be the same. So this tells me that both 9 is equal to 6a minus 3, and also that a is equal to 10a minus 18. Solve both of those. 12 equals 6a equals 2, or 18 equals 9a, a equals 2. Unsurprisingly, they better both be the same. That means that, so we're almost here. That means that this fact that my original polynomial factors to the following. That means that the original polynomial is equal to x squared plus 6x plus 10 times 2x minus 3. So the three zeros, so the zeros are the given 0, negative 3 plus I, its complex conjugate, minus 3 minus I, and from the linear term, 2x minus 3 equals 0, positive 3 halves.